Hello, welcome back. Today is lecture 55 and today we are going to talk about passive elements in an RF circuit. And although passive elements are very indispensable in MMIC, but they are also useful in MIC, hybrid MIC. You cannot just ignore the passive elements. So there are a lot of passive elements. We are going to talk about some aspects of them. Again, detailed treatment of passives would be a full semester course on its own, because there's so many things, including mathematical modeling, characterization, things like that. So we are going to understand as much as is required for this course. Okay, the basic flavor of what passives are and the basic concepts pertaining to them. So to the whiteboard here, passives are required not only for impedance matching. We saw in the last lecture that you have this inductor, capacitor. Those are passives with which you match the impedance. Impedance matching is a critical application of passives, but passives are also needed for things like filter. They are also needed for biasing, because whenever you have for instance a power amplifier, just giving an example, you have a bias network, you need to apply a certain bias, and passives are indispensable. And I told you both MMIC as well as non-MMIC designs, they rely on passives, and with higher frequency passives will tend to exhibit losses, and you will see that an inductor behaves like a capacitor at super high frequencies. A key thing to keep in mind in general is that the reactance coming from an inductor looks like that, whereas that coming from a capacitance looks like that, correct? So with higher and higher frequency, and this is impedance in a way, okay, so ignore the real part for now. So with higher and higher frequency, the impedance becomes larger. For an inductor, what it means is that a higher and higher frequency, it impedes, it's a high impedance for a AC signal. However, with higher and higher frequency, the impedance corresponding to a capacitor reduces, so it becomes like a short. At very high frequency, capacitors will act as a shunt path, it's a short, and at very high frequencies, inductor will basically become like, it will impede the flow of AC, so it will try to block it in a way. Okay, so just keep that in mind, that with higher frequency, if you have a dielectric, for instance, the capacitive coupling will now tend to dominate. Okay, this is a key factor, a key fact that you need to just keep in mind as we talk about many passives, as you will see. Okay, so the first passive that we have to talk about in general, it's not a passive but a critical component, is metal, because it is metal using which you are going to make inductor, using which you are going to make capacitor oftentimes, using which you are going to make transmission lines, via holes, interconnects and whatnot. So metal is most fundamental. Metal is metal, so if you have a width of W, a length of L and a thickness of T, if I'm sending current from this point to this point, what is the resistance? Resistance is the sheet resistance of the resistivity of the metal into the length divided by the cross sectional area of the metal along which the current is flowing, which is T into W. So if you want to reduce the resistance, you need to reduce the length, you need to increase the width, you need to increase the thickness. So if you increase the cross section of the device, of the metal stack, for instance the gate finger, if you make the gate finger thicker and wider, it becomes lower resistive, and that's good for you. But this W determines, for instance, your gate length. You cannot just arbitrarily reduce it or increase it. It's dictated by the gate length. But in transmission line also, you do not necessarily have a large degree of freedom in choosing W and all. You need to be within a range that is specified by the foundry or the process fabrication people, right? So the resistors are very critical. You need, for instance, resistors. You need metals to make resistors. You need metals to make all kinds of things, transmission line and so on and so forth. But let's talk about resistors. For instance, you will use a metal to make a resistor. It's one of the important ways to make a resistor. There are also other ways. For instance, in this picture here, I'm showing you a silicon CMOS based process, where the uniqueness in CMOS is that you have a lot of these dielectric interconnects, tungsten plugs. You can see the via holes. These are all back end of the line. The thickness of the layer becomes more and more as you go up, because you tend to carry more and more current as you go up. You are collecting current from different lines, and you're feeding them up as you go up, so the metal becomes thicker, bigger on the top. So you have these different metals that you're stacking up with different via holes, so that you can drain the current upward. You have so many interconnects and intermetallic dielectrics. You can implement a resistor. You need a resistor, by the way. It's not that you can live without a resistor. You need a resistor very much. Although I told you that in Smith chart impedance matching, you try to avoid resistive lines, you only go along the capacitive or the inductive lines, but don't get me wrong, resistors are very critical in many aspects. You need to put a resistor, for instance, to intentionally reduce the gain of a device. Why do you do that? So that your device becomes stable. just an example. Okay, so resistors are very critical, by the way. So if you want to implement a resistor in a CMOS process, you can either use a polysilicon as a resistor, you can use a diffused layer as a resistor. Both of them are not very good, because they tend to depend on temperature. With higher temperature, as you heat up with carrying higher current, your mobility will degrade in the diffusion resistance, and so it has a great temperature sensitivity. Polysilicon resistor is not as good resistor as a metal, of course, so a metal is always better. So in compound semiconductor, for instance, gallium arsenide or gallium nitride based MMIC and foundries, they use either a tantalum nitride or a nickel chrome alloy as the resistor. It's a metal, and tantalum nitride is also used, but nickel chrome has a relatively better temperature insensitivity, which means over a range of temperature that you need, say room temperature to around 200 degrees Celsius, your variation of the resistance of nickel chrome is actually lower than that of tantalum nitride. Okay, so nichrome is very widely used, and the typical resistances you can get would be a couple of tens of ohm per square. That's your sheet resistance. And a rule of thumb is that for nichrome, every micron of lateral width, which means if this is 1 micron, you are going to carry typically around 0.5 milliamps of current, for a given thickness, of course. So the thickness would be standard in a foundry. So typically nickel chrome is used as a metal resistor, but in CMOS process you can have a more elaborate back end of the line BOL, and you have large number of interconnect vias and things like that. Okay, so you use this tungsten plugs, for instance, to carry higher, integrate these different vias, and you need this low resistance metal such as copper or aluminum, so that your routing becomes easier. You don't want a high resistive metal, because the more you top you go, the more conductive your metal should be. You're carrying more current from multiple vias and multiple connect lines. Okay, now there is something very, very fundamental for metal at RF frequencies, which is called skin effect, and I think many of you already know what skin effect is. Don't go into the table here, I'll come to that quickly. Essentially what happens is that when you have a conductor, if I look at a cross section of a conductor, suppose it's a circle, it's a conductor. Okay, it's you can think of it as a circular line. The same thing happens for a transmission line on a semiconductor substrate also, but although I'm giving you an example of a circular line, it's a metallic line. It's not a hollow metallic line, it's a solid metallic line. Whenever you have an RF signal, it's an oscillating electric and magnetic field, correct? It's an oscillating electric magnetic field, and this oscillating electric magnetic field actually sets up a potential within the wire as it propagates. It's called back EMF. Okay, we're not going into the details of much of the physics here, but just suffices to understand that an oscillating electromagnetic field that is propagating along the conductor length, it creates a back potential because of the the field that it sets up. It creates a back potential which tries to oppose the flow of the current, and it's the highest at the center. The back EMF or the back potential that tries to resist the flow of current is the highest at the center and minimal at the periphery. So what happens is that as you increase the frequency to RF, microwave signals, the current will tend to flow along the periphery of the wire rather than throughout the wire. If you carry DC current or maybe a low frequency AC signal, few kilohertz or megahertz maybe, the entire wire will carry the current. The current will go uniformly throughout the wire. But as you increase the frequency, there is a back EMF that is developed because of this oscillating electromagnetic field, and it increases its frequency. So that back EMF will oppose the flow of current, maximum at the center, minimum towards the edge. So what happens is that if you look at the cross section, at the edge you will get most of the current that is flowing this direction, but in the center there is no current that is flowing, which means the current is confined to the edge of the wire or to the skin of the wire. So we call it skin effect, and the magnitude of the current drops rapidly with distance. So if I take like that, then what is the periphery in which this is confined? This is called the skin depth, which is represented by delta. Skin depth represents the distance from the outer edge at which the intensity of the current will drop to 1 by E. So we assume typically that almost all the current is flowing within that periphery of skin depth. So the skin depth is given by the square root of the resistivity of the metal, pi times frequency times the permeability. Now you see that F frequency comes in the denominator. So with higher frequency the skin depth becomes lower, which means, for instance, if I take gold and if I take 1 gigahertz of the RF signal, then the skin depth is 2.5 micron, which means if I take a gold cable like that, or even a rectangular like something like that, 2.5 micron from the periphery is all the current will flow, rest will not flow inside, which means I can have a wire which is just 2.5 micron and essentially 5 micron, So that 2.5 from this side, 2.5 from the other side, complete 5 micron, and that will carry all the current. I don't need like a 50 micron by 50 micron, or if I don't need a 50 micron diameter wire to carry 1 gigahertz signal of gold in a gold line, because the skin depth is only 2.5 micron, so everything will go in 2.5 micron. Now if I go to 10 gigahertz, if I consider 10 gigahertz of RF signal X band, the skin depth is around 0.8 micron or 800 nanometer, which means from the edge of the metal wire or the cable or whatever transmission line you are laying on the semiconductor substrate, only the 800 nanometer from the edge is going to conduct electricity. I am talking about the RF signal, the RF electricity, not the DC. Okay, so this skin depth essentially means that most of the inside of the metal is not carrying the RF signal, so the metal resistance for the RF signal actually significantly increases. So you can read through this whatever I am writing here. However, what it means is that if I give a certain aluminum line with a certain dimension, if I try to find out the DC resistance, it comes out to be suppose 50 milliohm. Now suppose I do find out the skin depth at 5 gigahertz, and from there I have to subtract the skin depth, if I have a rectangular line something like that, okay, and now I have a skin depth of certain thickness. So suppose this is the skin depth, which means current is only flowing in this. Can you see that? Current is only flowing in this. So I am going to have to subtract out this white part. So that's what I am doing here. Okay, so if I do that for the same line which had 50 milliohm resistance, the resistance for RF becomes almost 100 milliohm. It's like a 2 times increase in the resistance of the metal, and that's very, very concerning. So skin depth has to be taken into account. Now if at higher frequencies, if your skin depth becomes lower and lower, then why do you need thick metal layers? You remember these are thick metal layers, no? Why do you need thick metal layers? Because the skin depth pertains to only RF signals, not DC signals. You also carry DC signal along with the RF in most of these connectors or cables or transmission lines, and higher DC current can heat up, can lead to electromigration, can lead to huge series resistance. So you need thicker metals so that you have better routing, better current carrying capability, less heating, lower resistance, less electromigration, etc., etc. Your current density is low. So for that DC component you need to have thicker metal. Okay. So in gate metal, for instance, you don't carry much of a DC current, you only carry RF, so you don't need to thicken the gate. But source and drain metal pads will carry a lot of current, DC current also. So that's why you need to thicken the source and drain metal pads. Although RF signal will be there, but there is also DC bias, there is also DC current. So just keep that in mind. Okay. Now on chip transmission lines are very critical. We have already talked about microstrips, strip lines and CPW pads. Maybe I will recap them again. Amongst those, CPW, microstrip, strip lines are very commonly used. CPW is mostly used for on-wafer characterization, and in many cases strip lines and microstrips are quite widely used in an MMIC design. As you know, the transmission line itself does not cause a change in the magnitude of the reflection coefficient, they only introduces a phase. So they only rotate around the Smith chart, but it's an ideal lossless line. If you have a lossy line, then you will also introduce some loss, of course, right? So this is about transmission line, and for higher frequencies above a few gigahertz, it is very desirable that all your capacitor inductors are actually implemented by transmission lines and not by a component that you buy from the market, or a discrete component, right? So your transmission line such as a strip line or a microstrip is used to actually implement your inductor or capacitor in an MMIC. Okay. Now if I talk about a microstrip, there is a ground plane below, and then there is a top conductor here. The top conductor width is W, correct, and the substrate thickness is H. Now the dielectric constant of this substrate could be a semi-insulating, could be a lossy, I mean you do not want it to be lossy, is suppose epsilon r, that is your dielectric constant of the material on which you have, above you have air where the dielectric constant is 1. Now because your lines are actually spread out, you have electric lines but you also have magnetic lines going like that, so part of your electromagnetic wave exists in the air and that leads to some kind of loss, radiative loss, but overall combining the semiconductor substrate and the air above, because the fringing, the lines, the electromagnetic fields are existing both ways, you can define an effective dielectric constant taking into account that part of your EM waves are in the air and part of your EM waves are traveling in the substrate. So combined effect is a effective dielectric constant. Okay. Now how does this effective dielectric constant depend on the thickness of the semiconductor substrate or on the width of the line, for instance. Okay, so people do simulation to understand, because you also have to include fringing effects here. And this is a plot. So let's pause here for a second and understand what it shows. On the y-axis it shows the effective dielectric constant, and by y-axis I mean this dotted line. So this line, this line, this line, those are the effective dielectric constant. Maybe I can switch to red here. And on the right hand side y-axis you have the impedance, I would say the characteristic impedance of the line. This line has a characteristic impedance Z0, no, that's what precisely it's plotting here. And those are days, and days. These different plots, this one, those correspond to different dielectric constants of the semiconductor substrate. Suppose I have a gallium arsenide, maybe I have a gallium nitride, maybe I have indium phosphide. So dielectric constants are different. So those represent different dielectric constant, and this is a trend that you see. So what is the biggest and the most interesting trend that you see here? The most interesting trend that you see here is that if I increase W by H, which means I increase either the width of the conductor or I reduce the thickness of the semiconductor substrate, either way you will increase the W by H ratio. In that case your effective dielectric constant increases slightly. It means if I make a wider conductor and a thinner semiconductor substrate, okay, your dielectric constant increases slightly. It means more waves, more part of the EM waves will try to be inside the substrate. Whereas if you thin down the conductor and thicken the substrate, then there will be a lot of fringing, of course, and what you end up having is that you will have a lower effective dielectric constant. And this trend is opposite to that of characteristic impedance. So the characteristic impedance decreases. The characteristic impedance decreases when your W by H ratio increases. So if your conductor becomes wider and your substrate becomes thinner, then your characteristic impedance decreases. You can say the characteristic impedance increases with a lower W and a higher thicker H. That's what it means. With a thicker H, with a very thick semiconductor substrate and a very small thin conductor, you are going to increase the impedance, the characteristic impedance. Okay, the resistive part will take over here because your W is decreasing, by the way. And as you can see that with, of course, different, how it varies with different dielectric constants of the material. Okay, your thickness of the substrate could be a design parameter to some extent. You can choose to thin down the substrate, but again it may not always be available as a parameter to choose for a designer. The foundry might specify that this is your fixed H that you will have. W is your designer parameter because the width of the line that you are going to put here, it's on the designer, and there's a range over which you can put. You cannot arbitrarily put like a very arbitrarily thin or arbitrarily wider line. There's a range over which you can choose. Effective dielectric constant, basically it's a process parameter because it depends on the dielectric constant that they're going to use, silicon nitride for instance, or silicon oxide, whatever the foundry is going to use, that will determine your effective dielectric constant. And the method of deposition, whether you are depositing it by atomic layer deposition, whether you are depositing it by plasma enhanced chemical vapor deposition, whether you are depositing it by low pressure chemical vapor deposition. These are different techniques to deposit a dielectric film like a silicon nitride or silicon oxide or Al2O3, etc. Depending on the deposition techniques that you are going to use, the porosity, I would say the stress of the dielectric layer, okay, the density of the dielectric layer are also going to be different. So your dielectric constant that you get in the actual film is also going to be slightly different depending on the deposition condition, and that will also determine your effective dielectric constant. So just keep that in mind. Okay. Now microstrip, of course, if I look at this microstrip here, maybe I can again I can just you have a microstrip line like that here, and then you have a semiconductor substrate, and then this is your ground plane. Correct? This is a microstrip. The characteristic impedance is L by C. So here if I talk about a CMOS process, for instance, you will have an oxide here, silicon oxide. So this C is typically COX, the silicon oxide capacitive coupling to the substrate below. This L is the desired inductor. So if this ratio is very large, which means your characteristic impedance that you can measure is very large, which means your L is much larger than COX, which means your microstrip line is behaving more like an inductor. It's just a line. I'm not talking about a short line or an open line or whatever. It's just a microstrip line. If the characteristic impedance is very large, it means the inductive behavior dominates over the capacitive behavior of the line. And now How can you achieve that? How can you make it more inductive? There's an expression here. That expression goes like this, where this L is basically the length of the line. Of course, as you increase the length of the line, which is this, okay, as you increase the length of the line, your inductance is going to increase, but it also is going to increase your real estate. You are going to use up a lot of area in your wafer. So the way to increase the inductance is that this, look at this expression. This expression is 8H by W plus W by 4H. So inherently this factor dominates. So which means if I have higher W, if I have higher H means the thickness of the substrate is very thick. Or if I have lower W, which means I have a very narrow line, then I am going to increase my inductance. So I can make the microstrip line behave more and more as an inductor if I increase the thickness of the substrate and if I reduce the width, this width of the line. I can make it a thinner line. But there is a trade-off. See, this H is more or less fixed by the foundry. You cannot arbitrarily say that I need arbitrarily large H. The foundry will not agree to that because they have a certain process. A and W, you cannot make it very thin because you will increasingly increase the resistance when you make it thin, the DC resistance. So you're going to get a lot of series resistance that comes up. So you do not want that. So there's always a trade-off to play, and then you will settle down for something that is acceptable, and that's a trade-off. Okay. If your impedance is characteristic impedance is very low, that means your line, your L is much lower than C aux, which means your transmission line is predominantly capacitive in nature. And for that you can increase this factor, which is essentially you are going to increase W and reduce H. So if you look at this figure, if you increase the W very much and if you reduce the H, it's like a parallel plate capacitor, because the bottom ground plane is the global ground plane, right? So if you increase the top conductor very much, okay, like this, and you reduce the thickness, it's like a parallel plate capacitor, and so you are going to get a purely capacitive behavior with a very large capacitance and a low inductance, and that gives rise to a very low characteristic impedance of the line. Okay. Just like microstrip, you also have CPW, coplanar waveguide. I have already introduced this in many lectures already. I will not go again, but there is a central conductor line and there is a two ground plane on the side. You see, there are two ground planes on the side, and the central conductor line that you have here, and the ground plane that you have here, they are separated by a small distance s. Okay, and the conductor width is, for instance, W, which is W. You see that again much of the electromagnetic fields exist in the air, some of them also exist in the semiconductor substrate, but compared to a microstrip, in a CPW you actually have more radiation into the air. The field extends more into the air, so you have more radiative damage and more losses, and the CPW has two ground planes beside it, so the overall real estate that you have to sacrifice is actually much more than in a microstrip, because in microstrip you just have one line, but in CPW you have one line and two ground planes on both sides. So looking from the top, the amount of area that you have to sacrifice is pretty large. But the advantage here is that because the ground plane is located, this is a ground plane, this is a ground plane, the ground plane is located very close to the signal line, right? So essentially your parasitics pertaining to the ground connection could be low. You do not have to drill a via hole to the bottom, although people do that to reduce it further, inductance further, and to help carry heat or make sure the ground is same, etc., etc. But your ground is very close. Ground pads are very close to the actual current carrying conductor, and the ground pads are also in the same plane of the FET of the transistor. So your inherent parasitics corresponding to the ground connection would be lower than in a microstrip, where you have a global ground. You have a global ground, and there is no like a ground connection is far away. It's in the below substrate. Okay. So but other than that, the CPW properties are very much similar to that of microstrip properties in terms of the effective dielectric constant, okay, in terms of the characteristic impedance, how it varies with your W by H, more or less they stay the same, the behavior is the same, the CPW lines and the microstrip line. As I told you, CPW line is predominantly for enabling on wafer characterization using an RF probe station or a pulse heavy setup or a load pull, S parameter, etc. It's to enable on wafer measurement. Once you build the model of the devices, you do not necessarily need CPW pads in an actual MMIC or in a circuit. You can just have the discrete transistor there without this CPW pads, which are otherwise useful for on wafer characterization, and you can implement them in a chip because you already have modeled and understood the behavior of these devices. Okay. Now if I look at a CMOS process and not a compound semiconductor process, then there is an oxide here SiO2, and then there is this silicon substrate. Now although silicon substrate can be HR, HR stands for high resistivity silicon substrate, and by high resistivity silicon substrate you mean around 10,000 ohm centimeter of resistance, which is high resistance, but this is technically not high resistance for RF. At RF signal, at high frequency RF signals, it actually is very lossy, so that loss in the substrate is much higher than that in a semi insulating gallium arsenide or gallium nitride substrate. So silicon CMOS based processes will have a substrate loss, which you model in a parallel combination of the substrate resistance and the substrate capacitance, which are existing in shunt to each other. Okay, and both of these are existing in series with the oxide capacitance. The oxide capacitance will couple the signal on the top to the substrate below. So those, the oxide capacitance is going to be in series with a shunt value of a capacitive loss of the substrate and a resistive loss of the substrate. Okay, so these two factors, they represent the substrate loss. Okay, they represent the substrate loss, and you can see how the electromagnetic fields are propagating there. And of course, gate, this is the gate. For instance, there will always be a series resistance of the gate, there will always be a series inductance, and you have to use a distributed modeling network that you have a resistance, you have an inductor, and then you have a capacitor in parallel. Again you have a resistor, you have an inductor, you have a capacitor in parallel. You keep doing that. This is the distributed modeling. Okay, this is the distributed modeling. If your spacing between the ground plane and the conductor here S becomes infinity, it's like the ground planes are situated infinitely far away. It kind of mimics like the microstrip line. There's a ground on below. Okay, it mimics like the ground the microstrip line. Okay, next comes inductor, and inductors are very important because they occupy a large real estate, large area. You need a large area for inductor because you need higher values of inductances. To get higher values of inductances, you need larger areas of physical areas in the wafer of inductor, and you need larger L because that is what is demanded by maybe the biasing network, maybe the filter, maybe the impedance matching network. They might demand large L, and because of the large L you need to occupy a large real estate on the wafer. Okay, so not a good. So these are spiral inductors. You can see that the metal is spiraling. There is no metallic short here. It's spiraling, and then it has to come out, so you cannot do a short. So there is an underpass here. The metal is going below a dielectric and coming out here, so there is no metallic short here. The way to fabricate is of course that you have to put down the metal here, you have to cover it a dielectric and then etch the dielectric away from other parts, or maybe you leave it at that point and then you keep fabricating this spirals there, and finally you have to make a metal short from the outside to the metal that comes out from the below. Okay, and that makes it's an underpass. You do not have a metallic short here. So inductors are very essential for feeding biases or for impedance matching, and this is an important thing. For 5 to 50 gigahertz frequency range, for a 5 to 50 gigahertz frequency range, you can cover that with an inductor of value 0.1 to 10 nanohenry. This is the inductor values that you need to cover a frequency range of 5 to 50 gigahertz. Okay. Now if you have a large area, you are going to get a large inductance value, and a large inductance value, it may seem very good that you have a very large inductance value, except that it limits your self resonance frequency. What does self resonance frequency SRF mean? It is the maximum frequency at which your inductor will behave like an inductor. Beyond this frequency, your inductor behaves like a capacitor. I told you at the beginning of this talk today, the presentation. So your self resonance frequency is the ultimate theoretical limit or practical limit, you can say, beyond which your inductor is not an inductor anymore. So you need to have a large SRF or this self resonance frequency in order to enable your inductor to behave as an inductor over a large range of frequency. If you have a large L value, which means you have a large area, and you implement or you execute a large impedance value, you are going to get a lower self resonance frequency for sure, because you have a very large area. So capacitive coupling will be high to the substrate below. So when your capacitive coupling starts to play the primary role, your inductor is no longer an inductor. So your larger the area, more is the capacitive coupling, less is the inductive behavior, so less is the self resonance frequency. So the operation frequency also suffers. Okay. So transmission lines, if you have a transmission line which is straight, it also behaves like an inductor, except that there is no turn here. When you have turns like that, you can reinforce the inductance because of constructing coupling, matching, and so you tend to get more inductance out of it. But in a transmission line, there is no nearby lines that will reinforce the inductance. So you tend to get inductance, lower inductances. So if you need very small inductances like 0.1 nanohenry, transmission line is good. But if you want to go larger inductances, then transmission line will need a really large transmission length. Okay, so that's why you go for spiral inductor. Whenever the current is if you have a conductor like that, and if you have a conductor like that, if the current is flowing in the same direction, then you try to constructively reinforce the inductance. If the current flows in the opposite direction, then then what happens is that there is a destructive coupling in a way, and your inductance tends to be lowered. Okay, so just keep that in mind. So the way you model the inductor, the small signal model of an inductor, is that this is a desired inductance, the actual inductance that you need in that spiral inductor. This is a series resistor that will always be there with the series with the inductor, because this is your metal resistance, and this DC resistance will be there. You cannot avoid it. This CS represents the shunt capacitance, and this capacitance arises because of the capacitive coupling between the inductor lines. Like, these lines might have capacitive coupling, also because of the underpass. This underpass here, the metal line goes below the other metal line with a dielectric in separation. So those are in shunt or parallel. So that is your capacitance that is there. And then for a CMOS process, you have an oxide capacitance coupling to the bottom. Of course, in a 3.5 you don't have this, but in CMOS you have that. And the substrate is modeled by a shunt combination of a lossy, like a dielectric. There's a leaky substrate resistance, and then there's a substrate capacitance, which are both in shunt, and this is your small signal model, or you can say that not small signal, it's an equivalent model of your inductor. Okay, if equivalent model of the inductor. For a CMOS process, you have COX, which you couple, but in a compound semiconductor, you don't have that. Okay, and this substrate being lossy is again a more pertinent problem for CMOS, because your silicon is never high resistance typically. It always exhibits high losses at RF frequencies. But in a compound semiconductor such as gallium arsenide or gallium nitride, the substrate loss can be significantly suppressed because you have a truly semi-insulating gallium arsenide or gallium nitride substrate. Okay. So now with this background, what is very important to understand is the Q factor of an inductor. The Q factor does not only exist for inductor, the Q factor exists for many other things, such as an resonator maybe. Okay, so the Q factor actually is it's called quality factor, and it is a characteristic of resonators, inductors, many other components. Okay, and the definition will therefore vary from for inductor the definition will be different, for a resonator the definition will be different, but the general definition is that Q factor is the ratio of what you want divided by what you do not want, or what you reject, or what is not desirable. So this ratio should be high. What you want divided by what you do not want should be very high. Okay, and a higher Q factor means it's a good inductor. For instance, it means the inductor is behaving more and more like an ideal inductor if the Q factor is high. If the Q factor is low, then it means the inductor is not a true inductor. There is a lot of resistive losses, there is a lot of capacitive coupling that's happening. It's not a true inductor, it's not storing energy as best as it could. Okay, so the Q factor is very important, and the Q factor has three terms. The first term represents the resistive loss of the metallic line, because see, you are going to implement it in a metallic line, so ultimately there will be resistive losses in the metallic line. There will be resistive losses in the metallic line. So the resistive losses will determine the Q factor. The second factor is your substrate loss. For a gallium arsenide or gallium nitride semi-insulating substrate, this substrate loss factor could be 1, and so it does not play a role. But for CMOS based process, this could be lower than 1, say 0.5, 0.3, etc. That's a bad thing, because that is lowering the Q factor. This is the substrate loss, which will try to pull your Q factor down. And the third is your self resonance frequency, which is the highest frequency where you are going to operate. It's not the frequency, it basically relates to the frequency. It's the loss factor corresponding to the self resonance. So it should be 1 ideally, but at self resonance, at the point where your inductor stops behaving as working as an inductor and starts behaving as a capacitor, is called the self resonance frequency, and at that point this factor goes to 0, so that the total Q goes to 0. So the total Q factor of an inductor goes to 0 at the self resonance frequency. That means beyond that point your inductor is not an inductor, it is a capacitor. Okay, so just keep that in mind. So these are the three factors. What I'll do is that I'll wrap up today's lecture here, because in the next lecture then we can show you how the Q factor behaves as a function of frequency, what is the desired sweet spot where you need to operate the Q, where you can get a good Q factor. There's a peak Q factor and you want to operate around that Q factor, and one side you have substrate losses, and on the other side you have metal losses because of DC resistive lines. So between them you have a sweet spot where you need to operate, and it will behave more as an inductor at that point with a high Q factor, and it will store magnetic energy more efficiently, because an inductor ultimately has to store magnetic energy. A capacitor has to ultimately store electrical energy. We'll come to capacitor subsequently, but first we'll conclude our discussion on the inductor in the next class. Okay, so thank you for your time. I'll see you in the next lecture.